Swayam Prabha. Digital India. Educated India.
My question is, why are processors still stuck to this push pop paradigm? Like, why don't we see more accelerated or application specific instructions? I mean, why has ISA design been so stagnant that it is unable to take advantage of these new types of instructions? Basically, my question is that why am I still studying this push pop and load store architecture, which is and I'm still using it in my computers, whereas it was invented decades ago when computers were completely different.
So that's right. A lot of these instructions are very similar to those used back in 8086, right? And the main reason is legacy. You want the software or executables to still run. Okay. So you want compatibility, and there's a huge inertia to change that. So what do a CISC processing sort of philosophy, uh, what do? They keep adding specific complex instructions like SIMD kind of instructions and so on to the instruction set. You keep adding, but you don't subtract, you don't simplify. That's the CISC philosophy. And yeah, I mean, for performance, you have to do what the RISC processors are doing if you want to come close to the performance, right? You want to actually internally convert those into simpler instructions and schedule them. So that makes scheduling and so on easier. But what you're saying that newer instruction sets are not being designed and so on. So one hurdle is legacy. I mean, backward compatibility. You want programs that are written to be easily, without much effort, uh, converted or being able to run on these new processors, right? You don't want to design a processor that has no software for it. You have to, if you have to write all of the software from scratch, that's a huge no. Nobody will buy this processor. But on the other hand, there are newer architectures being designed. There are like open instruction set architectures like RISC-V, RISC-V is an example, where first of all you need support from a global community, because you have to rewrite everything. You have to write the C library, you have to write compilers, assemblers for it, and so on. So it's not just a matter of coming up with a nice instruction set. I mean, yeah, in a computer architecture course, if you are asked to design a nice instruction set, very elegant, nice, you can come up with that. But what about writing software for it, right? That's a big task. And if you want your architecture to be popular, you need to have people using it, and you need to have a wide variety of software available for it. So I think that's the reason that there is an inertia.
Yeah, that makes sense. Okay, thank you.
Okay, that is an interesting question. So yeah, then that's one reason why in this session I'm discussing the Spark architecture, because it's simpler to understand, it's more elegant, and so on. It's also similar to the other RISC processors that you might have seen. It's very similar to RISC-V or ARM in some sense. It has some other exotic things, like it has windowed registers and so on, which we will not discuss in this session. But the Spark architecture has some interesting things which I am not going to discuss in this session, because they are not relevant to understanding our basic fundamental ideas. Okay, so any questions from the rest of you? Please feel free to ask questions. Also, pause me at any time and ask questions. Okay. So where were we? We were trying to understand basically instruction execution, right? Whether it's a very early processor like 8085 or a more modern processor, essentially there's this picture that you have a register keeping track of the instruction. So instruction counter or a program counter, you have something to point to the stack, and you have these general purpose registers where you store your operands and your results. And by the way, the stack is very important. I mean, how else would you do recursion and function calls and so on? So stack is there to stay, right? Okay. So stack pointer, yeah, concept of a stack, having a stack pointer.
I don't know. I mean, it is possible. Basically, stack is coming from the stack-based virtual machine. That virtual machine is dictating why we are compiling to these move and add, right? You could argue that a register-based virtual machine can overcome this. Or no?
Yeah, but I mean, how would you very naturally implement recursion, for example, right? You don't know how many times the same function is being called. So you don't know at compile time how much space you need to allocate for sure. You can use the memory. Okay, it can be done, but essentially it's like having this feature is very useful if you think of the C programming model, right? You need a different programming model altogether to work without it. It ties in very naturally with how a C program is written basically. Okay, so we can come to that at the end of the session again. Okay. I don't think that was a very satisfactory explanation, but we'll come to that. Come
I
back to
mean,
that.
it's too much off the track. So yeah, we'll discuss it later. Thank you.
Okay. So here the basic instruction execution cycle is this is what it is, right? So when you reset your processor or when you power on the processor, PC is 0, right? Program counter. So you're pointing to the first instruction, and next PC is 4. Okay. So this may be a simplification, but imagine you have a processor and you have no other programs. You have no operating system, nothing. This is sometimes called a bare metal program. So it's running right on your processor, nothing else. You don't have an operating system. So when you power on by hardware, hardware design, so that PC is reset and it's 0. And next PC is PC plus 4. So what happens? You fetch the instruction fetch logic kicks in and it starts doing what it should do. It fetches the instruction at the location pointed to by PC. You decode the instruction, you execute it. That means you might keep something, store something in a register or add to registers and store the result in a register or something. If it is a certain kind of instruction like add, subtract and all, you might also modify the status flags. Like if the result is 0, you will set the 0 flag. Now, if the instruction you just fetched happened to be a branch instruction, then you might next have to move to a different location. But if not a branch, then you just say PC takes the value of next PC and next PC takes the value of next PC plus 4. So both move ahead by 4. If this was a branch instruction, then here when we decode and execute it, right, we might figure out where we are supposed to jump. For example, the instruction might be jump to the current value of PC plus 8. So what you do is we take the value of PC and apply this PC here and some value 8, some immediate operand 8 and so on, and then get the result, and that value should be our next branch target, right? So that value is then the result, like PC plus 8 for example, will be stored in next PC. Okay, and that's where we will branch to. So and then what? Finally repeat. So this is a simple instruction execution cycle in a processor. So let's look at some instructions, some type of instructions typically found in a RISC processor. Okay, you have a minimal set of load stores. So these are any instructions that access the memory. So maybe write a register value into the memory or read the value from a particular memory location and store it into a register, right? So load and store. So load is to load from the memory into a register. Store is to move some value from a register into some particular memory location. Now, if you have an x86 kind of instruction set, it supports a variety of memory addressing modes. Okay, say for example, you can do something like take the value in register R1 add to it some offset, like add to it some 8, value 8, and to this memory location store some immediate operand like something. So there's a bunch of complex things you can have in a load store instruction because it's a complex set of instructions, complex instruction set, right? But in a RISC architecture, you have very limited set of load store kind of instruction. So if you want to do something like this, you would break it down into multiple instructions. First take R1, then move 8 to R2, then R3 equal to R1 plus R2, something like this. And then do a load from memory location pointed by R3. So what one instruction did in a CISC instruction set, we are doing with multiple instructions, but we are getting the job done, right? So basically, there's a minimal set of memory access instructions, load store instructions, okay? Essentially, just putting something in a register to a particular location or fetching something from a location and putting it into a register, okay? Then you have add, subtract, and so on. Add to registers, subtract to registers, and so on. You can have bitwise and or bitwise shift. This is very useful, by the way, for multiplying and dividing by 2 and so on. So if you know, right, if you take a binary representation, if you shift it left, then it becomes it's like multiplying by 2 and so on. So this is very useful. So shift. Then you have branch instructions. So here is an example which is like BE, which says branch if equal to some location. That means before that, suppose there was a subtract instruction, subtract R1 and R2, store the result in R3. If R1 and R2 were equal, then after the subtract operation, the 0 flag would be set. The branch on equal instruction examines the 0 flag, and this branch is taken if the 0 flag is set, else it's not taken and you just go ahead with the flow as usual. So this can be used directly to implement code like, if A equal to B, then do something, else just continue from where you were here. So this naturally translates to this kind of instructions. Then you have trap instructions. So trap is something like when the user wants to cause an interrupt using an instruction, okay, do something similar to what an interrupt does. And why would we do that? Okay, so we'll see examples of where the trap instruction comes very useful in the afternoon session. Then there are these instructions for calling and saving and so on. So what's different from a branch and a call? In a branch, you go to some location, you change the PC. In a call, you might want to return back, right? In a function call, say you call some function, and when that function finishes, you must return back to where you were. So somehow you have to store what was the old value of PC somewhere, either in a register, separate register, or in a memory. And when you hit return, you have to copy this value, the next value of PC in PC, which was earlier there, back into PC so that you jump back here, correct? So call is slightly different from branch. So now suppose I want to see a demo of this, similar to the one I showed you, but for a Spark processor. Okay, so suppose I'm studying the instruction set of a Spark processor, and I want to take my simple program, C program, and I want to compile it and look at the machine code for a Spark. Can I do that? And how can I do that? Does anyone want to opine on that? Has anybody tried that in GCC, for example? So I have GCC, the compiler, running on a computer which has a x86 processor. So when it generates, it compiles, and when it generates the machine code, that machine code is meant for x86. Like I showed you, I showed the object dump, it is x86 instruction set. But if I want to generate it now for a Spark processor, what I need is a cross compiler. Okay. So basically, cross compiler is required when the host computer is different from the target. The host is where I'm running my compiler, right? The target is the machine or the processor for which I want to generate code. So if my host is x86, but the target is, let's say, Spark, I need to install a cross compiler. Now, I have put up a short tutorial on how you can install a cross compiler as an example for Spark and then write simple programs and so on. But if I want to run these programs, now I suppose I have a cross compiler. I take my simple C program, I compile it using the cross compiler, and I get some executable. These are machine instructions that can be understood by a Spark processor only. This won't run on my computer, right? So how do I view the output or something? I mean, I need to run it on a simulator then. I cannot run it on my machine because it won't understand these machine instructions, right? So I've set up a nice tutorial, and this kind of a cross compiler is very useful for those of you working in architecture or who want to do some research, because many times you may be writing assembly codes for a different processor and you may be using a different processor. So it's nice to try your hand at a cross compiler and just see what machine code looks like. And then to try it out, you need to run it on a simulator. Okay. Let me just take you through this. So this is kind of a step-by-step tutorial on how you can obtain a cross compiler, and how you can compile a simple program for Spark and run it, and how you can run it in GDB step by step, observing the result of each instruction. Okay, and this is very interesting. So let's see this quick demo because it's interesting. Are there any questions? So here is a simple assembly level program now for Spark. Okay, move to some global register G1. In Spark, the registers are named as G1, G2, and so on. These are the global registers, and then there are other registers, R9, R10, and so on. So notice that if you're using a different processor, the names of the register and so on change. So I'm moving 2 to G1, 3 to G2, storing the results in G3. So look at the assembly code. It also looks different from the one in x86. And then comparing and something and branch unequal. So here is a code. Okay. So what I can do is I want to compile it using a cross compiler. The cross compiler I have installed is called Spark Linux GCC. So this line will convert it into object code. Okay. The G flag is to retain all the comments and symbols for working with a debugger. So G flag is necessary. So this is an assembler. So next we generate an executable from it. This generates an executable called foo starting from the assembly program foo.s. Okay. Now there are instructions here for starting from a C program and getting to the executable. Okay. But that's fine. Let's just look at the object code. So just like I had the object dump utility, The Spark Linux object utility is for the cross compiler. Okay. So this again looks slightly bigger. Quite there are lots of other sections that I did not put in my assembly program. But here is the part which I wrote. Okay, this occurs at start. This is the start symbol. And it's essentially the same. Move 2 to G1, move 3 to G2, add, and so on. This part is same. Okay. And then some other things have been added. So if I write assembly, I can be pretty sure that you get what you want. If I write it in a high level program, then it's up to the compiler to convert that to different machine instructions. Is there a, I think, there a question? Is there a question? I can hear maybe one of the participants, maybe there is a question. No? Okay. So this is the code for a Spark processor. Now let's try to run it using GDB. Okay. So this is a demo. I'm not going to go into detail on how to use GDB, but I have provided some resources and tutorials links for how to understand and use GDB. Okay. So GDB allows you to step through the program one by one and see the effect line by line. But since this program is not running on my computer, it's meant for Spark, I need to use a simulator. So there are instructions on how to install the QEMU simulator here. Okay. And I'm just going to run it now. So what I need to do is to open two terminals. In the first terminal, I'm going to start my simulator and set it up for debugging with GDB for this particular executable. So the command is QEMU Spark. I'm going to start the simulator. So this starts the simulator. And in the other terminal, I'm going to open GDB. Okay. So this is GDB, it starts, and I want to attach it to the other process which is running in the other terminal. So I'm okay. So if you notice here, this was the assembly code, right? Move 2 to register G1, move 3 to register G2, add them, and so on. So I should be able to step through and observe what happens. So it is showing me the first line. So currently the execution is at the first line. Move 2 to G1. Okay. Now I want to see what happens. So there is a way in GDB to examine the registers. So you can say info reg G3 to see what is the value in the register G3, for example. Okay. So info reg G1 is currently 0. Now I can press S to step to the next instruction. So I press S. So that means this instruction is done now. And move to so want to see what's in G1. It should be value 2. That's right. So now if I press S again, it will step to the next instruction, which is move. This was move 3 to G2. So 3 has been moved into G2. The next one is to add. So step again. Okay. So now G3 should contain 5. So if I do info reg G3, it's 5 and so on. So this kind of allows us to step through the instructions at assembly level. Of course, GDB can also be used to step through instructions in a high level program like C and examine and set breakpoints. Like if you don't want to go line by line, let's say if you want to directly jump to a particular location, you can set a breakpoint and so on. So it's very useful. And the detailed tutorial is, I put it up here on this web page with some links also. Okay. Are there any questions about this? You can of course use a simulator with a graphical user interface. Like let's say you have a 8085 simulator. As you execute the assembly code, it will show you immediately the register values changing and so on. It's a visual, nice visual simulator. But if you don't have a simulator, or if you want something which is more powerful, then you can. I think in one of the later sessions, we would be going into more detail about KEMU. Are there any questions? No. All right.
Swapnil has unmuted. Yeah. Yep, please go ahead.
Thanks. Okay.
No, I was just asking what's the difference between Gem5 and QEMU?
Gem 5 is, I think, I don't want to answer that because I'm not very certain. I have not used Gem 5 much. I've heard of it and I have not used it. So I don't want to answer that question. It's yeah.
Sorry. Yeah.
Yeah, sure. So, but I think it's more targeted for microarchitectural research. So KEMU will not allow you to specify microarchitectural features like register windows and so on. If you want to model those, I think Gem 5 might allow it, but I have not used much Gem 5 much, so yeah, it's better I don't answer that question. Okay, thanks. So let's move on. So I want you to take a look again at the object file for that code, or maybe. This is the object code. Okay. Here is object dump for the Intel processor that I generated earlier. And here is the one for the Spark processor. Now, if you might notice some differences, first of all, here the instructions are of different lengths. This is 1 byte, this is 3 bytes, this is a 4-byte instruction, and so on. The sizes of each instruction vary. Here, all of the instructions are 32 bits long, that is 4 bytes long. Okay, every instruction is of the same length, which makes it easier for doing fetching and decoding and so on. Also, this address progression is then in increments of 4, whereas here it's different. The instruction starts on a different address, not necessarily 4 bytes apart. So that's one difference. You will also notice how the assembly is written is slightly different. But essentially, yeah, you will have move instructions here, and so on. So some of the instructions are very similar, some are different. Okay. So a small thing that you can notice. Okay. So coming back to the programmer's view, right? Now, if you take a closer look at the memory, you as a programmer will assume that you have all of these addresses available to you. Okay. And if you again take a look at the object dump here, you might see some names of sections, something beginning with a dot. So section.init, section.plt, okay, and so on. There is a section.text. So typically the name .text is used to indicate a chunk in memory which contains code, which contains machine level instructions. Okay, so .text is going to be the chunk in memory which has instructions. So typically if you write a C program and then you observe this kind of gives like a rough map of where things will be in memory, but this is not exactly going to be the same. The initial bits may change because of use of virtual memory, but the last might remain the same. So what it's saying is that this whatever is here should go into this section called .text, and whatever is in, let's say, so there are other sections. So basically it's telling the operating system that, hey, in memory there are these areas, so whatever follows this .text declaration should be in this chunk, whatever are variables etc should go in this chunk, and so on. So typically this is the memory layout for a C program, a programmer's view. Okay, so .text is basically the machine level instructions. .data are initialized data. These are variables which are all initialized to 0. Like suppose you declare an array, large array, which should be initialized to 0. So this is initialized 0 initialized data. Then you have the heap, an area which is dynamically growing if you call malloc and so on. Okay. So initially this heap may be empty, and if you keep calling malloc, this will grow downwards. Okay. Of course, there is a pointer which keeps track of the top of this. Similarly, the stack goes from bottom to top. So it starts from a very high address, and then you decrement the stack pointer to point to the top of the stack. Then you push something on stack, and you might decrement the stack pointer further, and so on. So it is growing from an high address to low address, and heap is growing this way. So can they meet? And what happens if they do? There can be problems, right? So the stack, if you keep calling a function, like say if you do recursion or if you declare a huge array on the stack, this can suddenly increase and overwrite some other areas, and that can happen. That is in fact something which is used for exploiting programs. Right. Have any of you heard of Stack Overflow attacks and so on? Please write in the chat window if you have heard of this Stack Overflow. Okay. So this is the basic layout that a user needs to see. So here are some exercises for you. So first is write different kinds of constructs in a C program, like if else or loops, while loops, for loops, function calls including recursion. Declare different kinds of variables, constant, static, arrays, and so on, and see what the generated assembly level code looks like using the object utility. Okay, this is a very interesting exercise to get an intuition of what happens exactly when your code compiles and it runs. Of course, some parts or some features may be hard to understand, but if you dig deeper, you will gain some interesting insights into this if you do this exercise. The second is to try and learn GDP. I've added links to tutorials and step through the execution for the code. So if you write a C program and then compile it, to just get the assembly level, the .s extension is the assembly level, and from assembly level you get the executable. So if you have all of these at your disposal, you can step through the execution line by line in the C program, one line at a time, or one line at a time in the assembly program, like I showed for the Spark case. So these are interesting exercises. I would recommend all of you to try it. You don't need the cross compiler though. The cross compiler is can be slightly tedious to install. You can just try it for the processor that you have, And if you are interested, you might find this cross compiler very useful if you are, for example, learning other architectures. So far we are here, right? We have done a basic review of instruction execution. So essentially this view, this particular view, as in what happens is there is a program counter and then you fetch the instruction and execute it. So this simple view, we have done a basic recap of, and we have seen some concrete examples and demos. So that's something interesting. But now we also understand the link between a C programmer's view and what gets actually executed on the processor. So how a C program typically is looks like when it is compiled into an executable. So we understand somewhat this link now. Okay, of course we have not gone much deep into the session, but I hope that it's somewhat clear where the variables go and where the code goes and so on. So now when you think of your laptop, right, it has an operating system running on it. So there are multiple processes which are sharing the main memory. So does the programmer need to be aware of other processes and their memory layout? So for example, if here is a main memory, let's say it's a 32-bit processor. So 2 to the power 32, that's 4 gigabytes. And that's as big as, let's say my RAM is 4 gigabytes. Okay. And at address 0, and this is the highest address. Now, if I look at the object dump, I might see addresses where the code is starting from very, very early address, almost address 0 or something, some early address, and then the stack is right here and so on. So I'm using all of this memory address space, right? But then there are so many other processes running on the system. So are they all somehow assuming that they have the entire address space at their disposal? And if I'm writing a program, and if there are other processes in the memory, then I should not, write here. So maybe this is the main memory, and part of it is already occupied when my process starts running. So I am given only this space. Tomorrow, if I run my program again, there is nothing, there's only one process running here, suppose, and I am given this space. So every time I run my program, it may be placed at a different location in the physical memory, right? It could happen depending on what other processes are running. So should my program change if I do that? How do I write a program that could run still the same, even if it is placed elsewhere in the main memory? Okay, so the second thing is, how can every process assume that it has access to almost the entire address space? So this is the memory that I have on my machine is the 4 GB. Okay, and here is one process, and the process has, let's say, many arrays, this, that, and stack, and so on. And the programmer assumes that they have all of the address space available to them from 00 to all f, all of the. And here is another process that also assumes the same, and here is another one that also assumes the same, and so on. They are all assuming that they have access to the entire address space, whereas the actual memory is limited. So how does that get taken care of? So this is done using virtual memory. So that's what we will discuss next. So before we move on, I would like to take questions, if any, because I would like to know if people find it too obvious, or is it not very obvious? Yeah. Yeah, that's right. So there is a comment on Stack Overflow. Okay, good. What about others? Are this memory layout has been discussed before? Are you aware of this? Any of the others can respond in the chat window. These things like this memory layout and so on, right? Okay, good. So let's move to discussing virtual memory now. So this is a basic review. It's meant to be basic, and as you progress in the summer school, especially in the second week, there will be sessions on more advanced topics. So this is a very basic review, and it's meant to make the understanding more solid. Okay. So we're going to take a break at 12:30. So let's start with virtual memory. So we know that there are multiple processes in the system and each one occupies core for a certain chunk of time. This gives an illusion of concurrently running processes, right? So what happens to these multiple processes when you think about the memory layout? Let's say this may be the layout for process 1, process 2, process 3, and so on. How do they occupy the main memory actually? And are they... So for example, when process 1 chunk ends here and process 2 is running, is process 1 still occupying some memory? Is it completely removed and put to the disk and so on? Okay, so what is the memory layout? So you might think that since we are time multiplexing between these processes very quickly, it may not be efficient to completely remove everything that belongs to P1, put it back on the disk for every time slice, and that's the case, right? We cannot swap out all of these things into the disk every time. So these remain in the main memory, but then how are they mapped to the physical memory? So we have these requirements. An executable needs to be relocatable. That means if it is placed at a different location in the physical memory, it should still somehow work. It needs to be portable. If it is executed on a system where there are different processes running or a different number of processes running, it should still work. The second requirement is the abstraction provided to the programmer, right? When you write a program, you should not have to worry about the exact physical memory layout, the addresses, and so on. Then you have multiple processes that should be able to share memory efficiently, right? And you need to provide some sort of a isolation from one process to the other. Let's say a user process should not be able to mess with the data or the code in the kernel. So a lot of these requirements, or all of these requirements, are met using the concept of virtual memory, the idea of virtual memory. And essentially what we do is we add a layer of indirection. So the address generated by the CPU, which is the value contained in the program counter and so on, is an address which is translated into a different physical address. So there is a layer of indirection, and there are two addresses. The virtual address, often called the logical address, and the physical address, which is the actual memory location in the main memory where it is placed. Right? The process which is running on the CPU still sees the virtual address space. Okay, so it sees that these are the addresses, and these are the addresses that will be present in the program counter register and so on. But there's something that is translating that address into a physical address. So we are going to discuss one type of virtual memory implementation called paging. So the basic idea is as follows. If you have physical memory, it is divided into contiguous chunks, aligned chunks called page frames. Okay, typically this is of size 4 KB. Okay, that's 2 to the power 12 bytes. So it's divided into these frames. Imagine that initially all these frames are empty. Now a processes memory layout. Okay, logical memory layout of a process is also divided into similar chunks called blocks or pages. And then some of these pages may be actually present in the memory, but not in a contiguous, not necessarily in a contiguous manner. Like page 1 here may be mapped to frame 1, page 2 may be mapped to frame 4, page 3 may be present in frame 5, and so on. Okay, so somebody needs to keep a track of where things are. So every process has a page table. So this is, for example, process 1's page table that says that block 1 is located in page frame 1, block 2 is located in page frame 4, and so on. So process table maintains a mapping between the pages and the frame numbers. So why do this? First thing is that some processes need not have a very large memory layout, right? They may have few maybe a very small process, not requiring a lot of memory. So all of these processes can coexist, and you can place these pages in frames as and where the frames are available. For example, if a next process is to be started and then frame 6 and 8 are empty, the pages for that process can be placed in 6 and 8. You don't need to have contiguous empty chunks in the physical memory. That's one advantage. Okay. Second is that this supports on-demand paging. That means only those pages that are recently required or being used are there in the physical memory, and those which are not being used or not recently used can be on disk, and you can fetch it from the disk and put it in the memory as required. Okay. So to do this, here's a page table of a process. You just add a valid bit to every entry. Now what this means is, for process 1, this is the memory layout, right? So page 1, 2, 3, 4, 5. Page 1 is present in frame 1. It's present. Page 2 is present and it's in frame 4. But page 3, the valid bit is 0. So I'm sorry, there's a typo here. This should be a don't care. This is not 5. Okay, this should be a don't care here. It's a typo. So page 3 is apparently not there anywhere in the physical memory. So valid bit is 0. So here's a simple idea by which you can utilize memory better, right? Okay, so you have a valid bit in every page table entry for a process that indicates whether that page is there or not. So what happens is that there is this translation unit, right? So when a process wants to access some memory locations, then there is a translation involved every time. So suppose process 2 is running and it's trying to access a memory location present in this chunk 2. Then it knows this page number. It will look up the page table entry, see the valid bit, which indicates that, hey, this page is actually present in the memory, and look at the frame. Frame number is 3. So it will go to this frame 3 and fetch the memory location from that page. So note that these are aligned 4 KB blocks. That means if what you want, the variable that you want to access, is located at the starting from the 3rd byte here, then the address will be starting from the 3rd byte here. So there is an offset which is the same. Okay, these are aligned blocks. Okay. So there is this demand paging. So what happens if we don't find something? So for example, process 2 tries to access some memory location which is meant to be in page 3, and page 3 is not present in physical memory because the valid bit is 0. So when you read this page table entry and you find the valid bit is 0, the processor figures out that this page is not mapped to physical memory. It will generate a fault, like a trap, okay, which will invoke or give the control to the operating system the operating system will read from the disk that particular page, put it in the memory, set the valid bit to 1, make up appropriate entry in here, do the translation and pass the control back to the user program. So what if the physical memory is all full and you want to fetch something which is not here? Okay, then you will have to swap something out. So you have to, if let's say pages 1 and 2 by both these processors are recently being read, and 3, 4, 5 and this 3 is not being accessed, then we might move out this page 4 back to disk and then fetch the page we want to read and put it back. So it is exactly like a cache in that sense. This is a cache of the recently used pages. Okay, so the physical memory acts like a cache for storing the recently used pages from the disk. So how do we replace? We might have some bits to indicate which was the page that was most recently used and so on. So there are replacement policies which are similar to how a cache works, a processor cache works. Okay, so when you want to write back something, if the page was written to, you may need to write it back to disk. If it was not modified, you just need to discard it. So there is a modified bit present in every page table entry. If that bit is 1, it means something in that page was modified, and when it needs to be swapped out to disk, it needs to be written back to disk. Okay. Now this kind of a indirection, okay, makes it easy to have access permissions on the page. So every page table entry could have some bits that indicate the access permissions. Okay, and these are, if you decode these, these are encoded to indicate that this page is read only or read write or executable or read only for user program but can be written by supervisor programs and so on. So basically these access permissions tell the processor what kind of access is allowed for the page. So if a user program tries to write something to a page which belongs to the kernel, for example, then when you try to translate, okay, so say this is a page 5 which actually is something that you cannot modify, not supposed to modify. So when process 1 tries to write to it, okay, you do the translation, you see the access permission does not match, so it will generate a fault and again the operating system will be invoked. So this provides a kind of protection to pages. So you have the job of the translation being done often by a memory management unit. It's not absolutely essential to have one, and there are ways to do this in software, but most modern processors have a memory management unit, which is hardware for translating a virtual address into a physical address. Okay, so what does it do? The MMU basically looks at the virtual address, refers to the page table, finds out the frame number, adds the offset and generates a physical address. Okay, now the MMU also checks the access permissions in the page. Okay, now here are some issues, right? So where are the page tables stored? Every process has to maintain a page table. So for every process, there is a table saying where in physical memory are each of its blocks mapped. If every process has to store such a page table, won't that mean that so if first of all it will require a lot of space in the memory, and secondly, if you have to translate, let's say you want to do a load from a particular address, so CPU generates a virtual address, the MMU first has to translate it. For that, it needs to read the page table entry, which is located in the main memory. So first obtain the page table entry, then translate that address into some physical address, and then go and actually do the load. So wouldn't it mean that every time you want to access the memory, you are actually doing two memory accesses to read the table, page table, from the main memory, right? So there are these two issues. So we will see how these two are addressed. Essentially, if you don't wish to do two accesses every time, the MMU must keep some recently used page table entries within the MMU, right? So it's like cache of recently used page table entries. This is often called the TLB, translation look aside buffer. It's a small cache of recently used page table entries. So suppose the MMU wants to translate a particular address. It reads the page table entry from the main memory. It fetches it and keeps a copy in the MMU in the small cache called the TLB. So next time if you want to translate the same address, the entry is already there in the MMU and you don't have to read it from the main memory. And often these page table entries are few, so a very small cache is enough. So generally the TLB is not as large in size as your normal processor cache. It's a very small amount of memory because the pages can be huge. So a small page table entry will allow you to translate many addresses which are contiguous. So there is a very small cache in the MMU for storing these recently used page table entries. So that takes care of the first problem, right? And again, this cache is the same as in the normal processor cache. Once it becomes full and you want to fetch another entry, you have to throw some older entry out. Okay, so it in that sense it acts like a cache. There are replacement. I mean, you don't have to replace if you are not modifying it, but if you have a limited number of entries you can store, then which one do you throw out and so on. So I think caches were already discussed briefly in yesterday's session, so we will not go over how cache operates or what is the basic idea, but this is a cache specifically for storing page table entries. The second aspect is all of these page tables, so one page table per processor, won't they occupy a large amount of space in memory? So that gets mitigated if you use kind of a hierarchical page tables. So we will see that we'll continue this in the next session. We'll see that after the break.